Jai Hind everyone, myself Ankita, Faculty of Department of IT, AKGEC. Today I will be going to discuss the topic genetic algorithm of MLT Unit 5, which is course of BTech 5th Sem, BCS 055. So, what is a genetic algorithm? Genetic algorithm is basically a search-based optimization technique which is used to solve problems on the principles of genetics and natural selection. So, it basically follows the problems of genetics and natural selections. Now, there are many problems in which it is difficult to find the solutions using our normal techniques. So it takes lifetime to solve. For such problems, we are using genetic algorithm. In this, we are trying to find out the near optimal solution for very difficult optimization problems. Right now, it basically uses the fundamentals of our genetics. How the principle of Darwinian theory of natural selection. So it is using such theories to find out the solution. Now we know that we have a search space. In search space, we have many solutions. Now from those solutions, we have to find out the most optimal solution. So the solution that will be fittest will be chosen as a best solution, as a best solution for the problem, right? So we are using the concept of your natural selection, that is crossover and mutations, which is applied to the solution to find out the best solution of the problem, right? Now, centered around the Darwinian theory of survival of the fittest, each individual thus is assigned a fitness value. So whatever solutions we have, it is considered as the individuals, right? Now these solutions, or we can say that individual, is selected on the basis of principles of natural selection. That is how fit that individual is, or how fit that solution is. And then those high fitness value solutions are given the crossover and mutations. Now after crossover and mutations, we will get the best solution. Now in this, we basically use these terminologies. First is the population. Population is a subset of the solutions we have for the problems. Chromosome represent the individual solution. A gene represents, suppose these are my solutions, and gene will represent the one element position of a chromosome or one solution, whereas allele will give you the value of that gene. Now how we have our normal problems. Now we have to convert that problems into a form that can be applied to an algorithm. So our problem that we see is known as phenotype, whereas then we convert it or encode it into a form so that it can be fed to the algorithm is known as your genotype. And the process of converting a phenotype into genotype is known as encoding. And when we give the solution, we have to decode the genotype into the phenotype. Now, for example, I have a bag, okay? I have a bag with a maximum capacity of suppose 10 kilos, right? Now, these are the items that I can keep in this bag. Now, my problem is that I have to keep the weight maximum to 5 kilos, and these items will have some individual weight. So, this very famous knapsack problem. In this, now how I am going to encode the solutions, right? So the solution could be now my phenotype of this is the combination of items that I will be keeping into the bag, right? Subject to maximum weight of 5 kilos. That is my phenotype. Now I have to convert that phenotype into a form so that it can be fed to the algorithm. That is the genotype. So what I will do? I will use a binary representation. So 1 means the presence of the element and 0 means the absence of the element, right? So this is how I can find out various combinations of these items, and these will form the population of solutions, right? Now next is the fitness function. Now I have these solutions with me. Now these solutions, whether they are good or bad, whether they should be proceeded further or not, it is dependent on their fitness values. Now, fitness value will tell me whether this solution is fit or not. For that, I will be using a fitness function or evaluation function, and then I will be selecting my solution. Then, after finding out the fitness values of the solutions, and then I will be selecting them as parents. Then I will perform the genetic operators on them. What are genetic operators? These are the operators which change the genetic composition of the offspring, and they include crossover and mutation and selection. So These are the various operators that we apply on the population of solutions. Now, what is the structure of your genetic algorithm? Now, this is the whole process that we are using to, you can say, to do the apply the genetic algorithm on the problem. The first is population initialization. Now, it means in this phase, I have initialized my population of solution, right? Then fitness function calculation. Then I will be, for each of my solution, I will be calculating the fitness function. Okay. After calculating the fitness function, I will be selecting the parent population that will be used to perform these. What are these? These are your genetic operators. Okay. So I will be applying these genetic operators on my population, right? It could be crossover and mutation. And after that, whatever, I will then select my solution, best solution. And it will terminate and return the best. After the many iterations, it will return me the best solution so far, right? So this was just brief how I have introduced. Now I will be discussing in detail. Now, first is encoding. As I have told you, I have my set of solutions that is represented as phenotype. Now, I have to convert my phenotype into a form so that it can be fed to the algorithms. Now, that is known as genotype. So, encoding is the process of converting phenotype into your genotype. So, as I have discussed in before, for example, I have to find out a best combination of items that I could put in my bag subject to maximum weight of 5 kilos, and I have to maximize my utility. So, this is my, so I could have a combination like I have to put the book, laptop. So, how this could be represented into a format so that it can be fed into my algorithm. So, genetic algorithm works on two types of spaces, that is genotype and the phenotype. The genotype is the coding space and phenotype is the solution space. Now, this transformation is known as, from genetic operators, this is known as decoding. This will represent my genotype, represent my coding space is my genotype, and this is my phenotype. The process of converting the phenotype to genotype is known as the encoding. Vice versa is known as decoding. Now, there are various types of encoding, that is permutation encoding, binary encoding, and the value encoding. Now, when we talk about this is a binary encoding. Binary encoding says it is the most common form of encoding, and it says that I have to represent as a form of a binary number, that is 1 or 0. 1 will say the presence and 0 will say the absence. Now, see, this is my one population. Solution of one population. In this encoding, each bit shows some characteristics of a solution. On the other side, the binary string represents the value. Now, you can say the example that we have seen so far of the knapsack problem, we have represented my phenotype as a binary. Now, similarly, we can convert into octal and hexadecimal. Octal encoding says in this encoding, each string uses a set of octal numbers. In binary numbers, we were using 1 and 0. Whereas in octal numbers, I will be using from 0 to 7. Similarly, in hexadecimal, I will be taking the values from 0 to 9 and A to F. Next type is your permutation encoding. Now, permutation means the order in which my items are placed, right? For example, there are many problems in which the order is important. For example, traveling salesman problem, I have to find out the best combination of the cities I can travel through. So, I have 5 cities, so it could be encoded as A, B, C, D, E. I will be giving them numbers 1, 2, 3, 4 and 5. So, one possible chromosome could be I visit 3, 5, 2, 4. So, 3 is C, 5 is E, 2 is B, A, 4 is D, right? So, this represent, this is my phenotype, this is my genotype. So, this is how I am representing my solution as the various combinations or permutations of my values, right? Then is value encoding. This is used in the solutions. Variables can take real numbers, characteristics or symbols and it is not limited. So if I have some value to represent, I can use value encoding. For example, I have to optimize the function f, x, y, z, and a chromosome could be the values of these x, y, z. What are the main possible values of x, y, z? So these are the few encoding techniques by which I am converting the solution space to the the coding space. Now, once I have achieved I have converted or represented my solutions and in a format that can be fed into the algorithm, my next step is to find out the fitness of each of these solutions. Now, the fitness function takes the candidate solution to the problem as input and produces the results at the statement as the output. So, what my purpose of this step is to find out the fitness of each of these solution values. Okay. Now, how this solution is good? For that, I will be using a fitness function. Now, this fitness function should have a specific characteristic that it should be fast to compute, right? It should not take time to compute, obviously, because this is just one step. Now, if I have to find out the fitness value of all of these solutions, now my fitness function should be fast enough that it give me the values quick, okay? And it also should quantitatively measure how fit a given solution is. It should not give me an abstract representation. It should give me some numbers so that I can judge, yes, this solution is fitter than the other solution. So for some complex problems, it not be possible to directly apply the fitness function to calculate the fitness values. In such cases, we use fitness approximation. So sometimes it's not possible that we give exact values through the fitness function. In such cases, we use fitness approximation. Next is after calculating, now we have represented the solution in our genotype, and next step was to give them a number based on their capability, and that number is known as the fitness number. Okay. Now, after selecting the parents, noting every population, now our next step is to apply the genetic operators. Now, genetic operators are used in genetic algorithm to guide the algorithm toward the solution. So, now we have to proceed further to the solution. Now, here these operators alter the gene composition of the offspring. They work in conjunction with each other. So, these are the three methods by which we apply to find the most optimal solution. First is your selection, crossover, and mutation. Now, what does selection mean? Selection means like if you have studied about Darwinian theory in your school days, you know survival of the fittest. It means when we were as a human were evolving, the fitter individuals mated and give rise to next generation. In the same way, the solutions which have better fitness values will be selected and then they will be used to make the most optimal solution. The same way we have the selection. So in this, it's decide which individuals from current population will be chosen to reproduce and create the next generation. The main objective is to favor the best solution. So whatever solution that we are seeing now, we have to select the best solution from them, and then we have to use them to create the future generations. Okay. So here the chromosomes are chosen as parents based on their fitness, and higher fitness, higher selection probability. Now there are various methods by which I select the fitness, I select the parents. So here basically we are selecting the parent population from the set of population which can be used further for finding out the most optimal solution. And for that I have these 4 techniques. First is your fitness proportionate selection technique, tournament selection technique, rank selection, and the random selection. Now first is your fitness proportionate selection, which is also known as roulette wheel selection. Now here what it does, we have a roulette wheel, and those solutions who have better fitness will be given more space in the roulette wheel, whereas those solutions which will be having less fitness will be giving lesser space. For example, if my A's fitness is 8.2 of 100, so it will be giving them 82% chance. Okay. If B's fitness is 30.2, it will give him 32% chance. So the space, and we will spin this roulette wheel, and wherever it will stop, we will choose that population. So that is your roulette wheels. Obviously, those population or those population solutions which will have the better fitness value will have the more chances to be selected as parents. Next is tournament selection. In what we does that we randomly pick a small k individuals. So from here I will pick randomly k individuals. Suppose here k is 3. Now I have selected randomly 3 individuals, and out of these 3 individuals I will see whose fitness value is more. So the most one I will select. For example, if A has fitness value of 5, E have the fitness value of 2, and T is the fitness value of 2. So obviously I will be selecting A as my parent. Next is rank selection. So based on the fitness value of my solution, I will be ranking them, and obviously the solutions which have higher rank will be given priority for selection. It mimics the biological reproduction. So as we have parents, now parents together make the child. In the same way, we have a parent 1 and parent 2. We perform crossover operation between these two parents. Now there are various ways by which we can do the crossover. The first is your single point crossover. So now suppose my parent 1 is represented like this, parent 2 is represented like this, and I have to perform single point crossover. So I will choose any random crossover point, and what I will do, I will exchange them like this. Okay. So this portion and this portion will be together form one offspring, and again this portion and this portion will form the second offspring. So here we are getting 2 offspring. Now there are also multi-point crossovers, in which what I will do, I will have 2 crossover points and I will interchange them. So here also I get 2. Then I have uniform crossover, in which what I will do, I will choose 1 gene from here, 1 gene from here, 1 gene from here, 1 gene from here, like this. So I will be having some uniform crossover points. So these are the various crossover points that we are using to generate offspring from the parent population. Selection will, what it will do? Selection will help me select the parent population from a set of populations I have. I have one population which have many solutions. Based on the fitness values, I will be selecting parent solutions. Now, after selecting the parent solutions, I will be performing the crossover operation. It is similar to the survival theory of the fittest, okay, in which the fitter individuals mated to give rise to the offspring. Okay. Now, after getting the children, they might not be the best. So next step is to do some mutation. Now mutation is a process in which new solutions is obtained by introducing a small random tweak. So in our human also we have certain mutations where some genes in our gene pool get changed. So in the same manner, what we are doing, whatever solutions we have obtained after crossover, we will be tweaking some of the genes. So mutations perform exploration of search space and is very essential for genetic algorithm to convert successfully. Now this is a main problem of genetic algorithm, that it does not, we're not able to understand where do we need to stop, where to we have the most optimal solution. So mutation help us to converge that process quickly. So you can see I have a before mutation, this is my solution. Now after mutation, what I have done, I have changed my this only one gene I have changed and converted into E to F. Next is how we are doing the mutation. Now there are various mutation operators. There are various mutation operators that we are using. The first one is your bit flip mutation and the random resetting and swap mutation. Now in bit flip mutation, what we do, this is my one, this is my solution. So what I will do, this is a binary encoded solution and I have to do the mutation. What I will do, I will just flip one gene, that is 1 to 0. In swap mutation, what I can do, I can exchange the values of the 2 genes. From at 2, I will get 6, and from 6, I will get 2. Then scramble, it will just scramble them. Then inverted mutation, it will invert the values. So this is how we are performing some random tweaks in my solution in the hope that I will get the best solution. Now, till when I have to, go through this process of selection, crossover and mutation. So that is my termination condition. How should I terminate? For that, there are 3 conditions First is no improvement condition. So I have to verify at each stage whether my solution is getting better with each cycle or not, right? Second is, second might be that I will do this at 5 times. So I have already fixed my values, that is fixed generation condition, and then target fitness condition. So once I received a fitness value of say 100, I will stop. So these are the 3 ways by which I can decide whether I have got the best solution or not. Now for that, I will keep a counter. Now counter will say if I am getting some improvement generation by generation, then okay, I will increment it, otherwise I will not. So if any offspring has better fitness value, the counter is reset to 0. And if suppose my counter is 0, I got no better solution, so I will exceed the counter by 1. Now in next iteration also, I'm not getting a better solution, so it will increment by 1, that is 2. Okay, but if I find out in one of the generation I receive some changes, some positive changes, so what I will do, I will reset the counter to 0. So if this value reached some say value 5, then I will stop. So in this way, we can say that we will keep on doing this iteration till we counter is reach to some specific value of this. So the choice of termination condition is problem specific. So we have to decide beforehand only when we will be going to stop. So that was your genetic algorithm. Okay. Hope you understand. Thank you.